Number one is called the VSEPR theory. VSEPR theory. Second one, valence bond. And the third one is molecular orbital. Now, we have time to cover the first two, but the third one, if the circumstances present itself in a course in the future, then review it. It's not that big a deal. In my history, the VSEPR and the valence bond theory have sufficed to explain all of the molecular interactions and structures that I've always needed to deal with. At any rate, so we will just focus on these two and leave that one off of the list for right now. Okay, so getting into the VSEPR, this is an acronym which means valence shell. Okay, that's the outer shell. Electron pair. Repulsion theory. Consider a molecule AX2, and it has a structural formula: X bonded to A bonded to X, like that, whatever. And as we know now, the bonds here, this is an electron pair in there. Two electrons over here, two electrons on the left and two on the right. One of the things that's commonly understood is the charge on the electron. So when we look at a bond, we assume it has a negative charge on it. So it's a negative field that surrounds the bond between A and X. And like charge, and because like charges repel, the bonds will repel to positions in space that minimize what we call repulsion energy. So in giving you that statement, I think you can appreciate negative repulsion. So reinforce this idea: if we had a structure like this, was bent like this or bent like this, the repulsion between the negative charges in the bonds would force these back to a linear configuration, which is the minimum. This is the position in space which would minimize the repulsion of those bond structures. You know what 180 degrees is, like difference like that. this is a natural phenomenon. Opposites attract and likes repel. Well, if you have negative charges on both sides and they repel with equal force, then they're going to repel to positions that will minimize that repulsion effect. It's like a coil spring. If you bend it and then turn it loose, it will return to a horizontal position. And so this is kind of an analogy that you might be able to relate to more easily than the idea of structural repulsions. But it acts like a spring. It goes back to a straight line or a 180-degree angle between the bonds. That's why it's called the VSEPR. Valence shells, electron pairs, repulsion. So the repulsion is pushing it into the structure that it would be most stable in. And so you won't find structures, there's other points to be made here, but you won't find a structure like this if all you have is bonds on either side of a central element. Okay. Because of the bond-bond repulsion, the geometries associated with molecules are limited to 7 what we call parent structures. About central elements. Able to support bonded substrates. We just saw one, and that was a linear geometry, and is given an AX2 empirical formula, and which gives us a central element, A, and attachments we call substrates. Okay, now these are referred to in this as bonded pairs in the structure you're looking at. In that you can just call them bonded pairs. Now, as we go through some of the others and later, you'll see that you can have both bonded pairs supporting a substrate attachment and non-bonded pairs on the central element. And we'll get to that shortly. But if you have a structure that does not have any non-bonded pairs, no free electrons, no free pairs, you will have a 180-degree bond angle, and sometimes it's listed theta B, which is the symbology for bond angle, is 180 degrees for a linear structure and represents the bond angle between those bonds. That's essentially what it is. Now, I said there were 7 parent structures. The second one in this collection is called a trigonal planar. Yes, you've got to learn all this. Knuckle down. And involves 3 substrate attachments to the central element. Now, it's a planar structure and involves, like I say, 3 substrates attached to the central element. And where that's the A in the middle, and usually written horizontally, A, X, and X, if you're looking down from the top of it. And each one of these is 120-degree bond angles. In their structure. These are your substrates that are attached to the central element. I'm going to go all through 7 of them, then we'll talk about derivatives. You can follow me on that handout I gave you. You look at the parent structures. The third one is tetrahedral. Geometry, if you want to, and involves AX4, or 4 substrates attached. Now, again, these are natural geometries that result from the bond-bond repulsion theory. The real bonds are repelling each other. And so if you have 4 substrates attached to a central element, it's going to go into a tetrahedral geometry. And what that means is that a tetrahedron, if you draw a straight line down, then a obtuse angle, and then another one coming off here, and then one like this, and then these are your substrates, the black dots. Your central element, of course, is that one in the center, and these black dots. And if you draw dots to them, you'll see a regular tetrahedron. And of course, each one of these is a bonded pair, and they repel each other to positions that generate this tetrahedral geometry around that central element. Now, up to this point, the central elements or elements conform to whatever they are on the periodic table. The octet rules, and we'll see some that are in group 3 and group 2 shortly. But beyond this, we will depart from the octet rule, and it will have more than 8 electrons in the central element. Some of them have 10, some of them have 12, some of them have 14. And so, going past the tetrahedral group, we run into what we call a trigonal bipyramid. Or trigonal bipyramidal geometry, some people. And it is an AX5. And you can see real quick that 5 attachments to the central element violates the octet rule real fast. Now, let me show you how I draw it. You draw whatever. Start with, I tell students, start with a lazy triangle. That's something that looks like that. Is that an isosceles or something? But at any rate, one side's longer than the other. You don't have equal sides. And then right through the middle, you draw a vertical line up and one straight down. Like that. So lazy triangle, up and down lines. And then from the this is your central element, the black dot, and it will have bonds going or radiating from that central element out to your substrates. And the vertical lines are also attached to substrates. 1, 2, 3, 4, 5. And you can connect these, and hopefully my artistic endeavor will reveal a bipyramidal system, 2 pyramids connected back to back, and it's called trigonal bipyramid, meaning 2 pyramids. These again are parent structures, and later on we'll show you how the derived structures come out of this. The trigonal bipyramid, then the next level up is an AX6, which is called an octahedral geometry. and is based on a central element and 6 substrates attached to the central element. Now, in drawing the octahedral, pretty much the same idea, except instead of a triangle, we start with a lazy square. That's what I tell students. One is kind of leaning over like that, and then we'll draw a vertical to the center, as I'm showing you here. Put the central element, the A, right here in the middle, and then radiate out to the points of your lazy triangle, and put your substrates. It'll show you 6 substrates, and this is called a regular octahedron. You can see that. Like that. So I've got some graphics that are a little more visual. Hopefully they're a little bit better for each of you. Here shows how the pairs arrange themselves in space to minimize that repulsion energy. 180 degrees, and this one, there's 120. When you get to the tetrahedral, learn 109.5 degrees if all the attachments are the same. If you change the attachment, you will change that bond angle a little bit, and I'll show you that as we get into those geometries. Here's your trigonobipyramid, and of course it's a triangular, like a trigonoplanar, 120 degrees, and then you have 90 degrees on the verticals, obviously. And same way here, there are 90 degrees everywhere in the octahedron. So you can see in this diagram how that, let's see if I can focus it a little better for you. Maybe that helps. And you see the idea of the VSEPR idea, valence shell electron pair repulsion. Now, when we say valence, what happens, this may have several rings for a core, but the event of repulsion occurs because the valence shell undergoes a change. It undergoes a change to what we call pre-bonding orbitals. And those pre-bonding orbitals are said to be hybridized, and they will all look alike, and they will assume positions in space that minimize the repulsion idea. And then we'll get to that on how to determine that. Okay, so the problems you'll run into on test day are you'll be given a molecule formula like this and say, okay, what's the geometry though? What is the geometry of the molecule with those substrates attached to it? Well, or these and so forth. And then more complex molecules, and I'll save that to the end of this little lecture. You need 2 things in this to determine a geometry. 1, the number of bonded pairs, or electron pairs, bonded pairs. And 2, the number of non-bonded pairs. It's very straight. But it's going to take some repetition to kind of instill the method that I'm showing you into your psyche. So you'll see the routine of it. So we will start with the beryllium chloride. And again, you need 2 things. You need the bonded pair and the non-bonded pair. Well, the bonded pairs are gimme. It's easy. How many things do you see attached to the central element? 2. So that indicates 2 bonded pairs. Or simply 2 covalent bonds in that structure. Now the other part of this is the number of non-bonded pairs. And that has a little formula with it, and it's not hard to find to do this. It's like the AVO-BEC, except the formula has to be defined a little bit different, so don't get it confused with the AVO-BEC that we did yesterday. But the number of bonded pairs is valence number minus substrate number over 2. Now you already know how to do valence. Let's just add up the valence electrons based on the position on the periodic chart. Substrate is just working with the substrates when they're bonded. It's either, like this case, you have 2 substrates bonded, its substrate number would be full at 8. If it's hydrogen sitting there, it'd be full at 2. So you would have a 2 times 8. So the valence number is beryllium plus 2 chlorides, chlorides, and that's a 1 times 2 because it's in group 2 on the periodic chart, plus 2 times 7 because chlorine's in group 7 on the periodic chart. That's 16 is the valence number. It actually is 16 valence electrons, as you know. The substrate number is only the attachments. That's all you want to worry with, the attachments. And since there are 2 attachments, that's 2 chlorides, and when they're full, they are full at 8 electrons, and that's 16. So the number of non-bonded pairs is valence minus substrate over 2, 16 minus 16 over 2, which is 0 over 2, and 0 non-bonded pairs. And the bonded pairs are up here. Now, to define the parent structure, let's do it. Bonded pairs plus non-bonded pairs equal parent. That means the bonded pairs, there are 2, plus non-bonded pairs 0, and that gives you 2. Well, what that means, it is 2 substrates attached to the central element, and if you have an AX2, it's linear. Okay? So we can draw our molecule like this, put in the appropriate non-bonded pairs around chloride, fill up the octet for chloride, and we know that this is a 180-degree bond angle between the bonds on that one, and they will repel to a linear structure. So beryllium dichloride is a linear molecule. Okay? Now the same thing will be applied to the next example. We'll use hydrogen in this one, boron trihydride. So we need 2 things, right? We need the number of bonded pairs and the number of non-bonded pairs. So you can look at it and tell how many bonded pairs you have. So there are 2. The non-bonded pairs is valence minus substrate over 2. So you have to figure the valence number, boron, group 3, plus 3 hydrogens, group 1. So you have 1 times 3 plus 3 times 1, and that's net 6. Substrate number is your only your attachments, 3 hydrogens, and when hydrogen is full, it's 2. Hang on. 2. That's also 6. And so putting those 2 into this formula, 6 minus 6 over 2, gives you a 0 non-bonded pairs. So, thank you. 0 non-bonded pair. So, in order to determine the parent structure, it's your bonded pairs plus your non-bonded pairs. And again, 3 plus 0, gives you a 3, which means the parent is an AX3 parent, which is trigonal planar. And so our molecule BH3 would be drawn H in this geometry, 120 degrees, and electron pairs repelling each other to 120 degree bond angles. All the way around. So you defined your geometry for the parent, and that just happens, the parent and geometry are the same. So let's look at SNCl2, called tin dichloride or stannous chloride. Now the question is this a linear molecule, AX2, or is it something else? Actually, it's something else. So we have to go through the same process of evaluation, bonded pairs, non-bonded pairs, etc. So again, the bonded pairs, 2, see if I can get that right now, and the non-bonded pairs is valence minus substrate over 2. So we have the valence numbers, the 10 plus 2 chlorides, stannous, are 10s in group 4. If you look down on group 4 on the periodic chart, so it's 1 times 4, and again chlorides in group 7, 18. These are valence numbers. Substrates only have 2 attachments, and so when those chlorides are full, they fill at 8, right? Everything's 8 or 2. Okay, and that's 16. So now we take the valence and substrate and put it into our formula up here, 18 minus 16 over 2, and that gives us 2 over 2, and it gives us 1 non-bonded pair. So we have 2 bonded pairs and a non-bonded pair to put into our molecule now. So the parent is the first thing you want to determine because it sets the pattern for the geometry. Bonded pairs plus non-bonded pairs, that would be 2 plus 1 is 3, which means the parent is an AX3 or trigonal planar. So you draw it out like this. You got 10 and you've got 3 electron pairs. Remember, it's not the substrates that are repelling, guys. It's the bonds that are repelling. This parent tells you how many bonds are repelling. And there are 3 electron pair repulsions, VSEPR, taking place. So we have 3 bonds assuming positions in space that minimize repulsion. But we only have 2 attachments this time. And 1 is left with an electron pair, a non-bonded pair. And these are, of course, the bonded pairs that show up in the structure. And because of this natural geometry it takes, the trigonal planar forces this into a bent geometry. Now, the geometry term, if you look at the handout, you'll see where it's an AX2E, where the substrates are 2 and E is the electron pair. But the geometry, listen to this, the geometry is only named in terms of the substrate attachments. And because of that, it's a bent geometry from a trigonal planar parent. So only the substrate and the angle it makes with the central element defines whatever that final geometry is. And you can look at it and say, well, that's bent. And so the other bond in there, or the other electron pair, is just left kind of by itself, free pair, as a repelling pair. Now, one of the things that you want to kind of watch for as we go through this is that when you have a non-bonded pair in here like that, that's a very strong negative charge and functions to even repel more. Non-bonded pairs increase repulsion, or bonded pairs. So you're no longer in 120 degrees. Actually, you're less than 120 degrees between those bonds now, because that non-bonded pair will kind of shove down on the bonded pairs. And you'll see more about this as we get deeper into the other kinds of structures. From your handout, you have linear geometries is an AX2 only. So you only have one, you don't have any derivatives here. It's just 180 degrees between the bonds and that's it. But when you get to trigonoplanar, that's your AX3 base. And so you start here, and then if you have all three, that is the parent and the geometry. However, if whatever molecule you have turns out to be an AX2E, then that geometry you have to draw one of the bars in that diagram as having a non-bonded pair, and then your substrates would have whatever that is, and that's a bent geometry. So an AX2E is a bent geometry. And the parent and the geometry are not the same in this case. Only if when you work out the valence, the bonded pairs, non-bonded pairs, and substrates, and it shows out to be an AX3 in the molecule, then yeah, that's the same as the parent structure. But if you have non-bonded pairs, it ain't the same as the parent structure. That's the point. Now, we move from here to the tetrahedral. Parent is what I should say. And of course, that's an AX4 structure, and that's your tetrahedral. So you'd have something like this to begin with. It gives you the regular tetrahedron central element. And if you have an AX4 parent, then you have 4 attachments. But you can also substitute a non-bonded pair in for one of the X's. And so while you still must draw the tetrahedron, you can put a non-bonded pair, and then you have 3. And so this is an AX3E geometry, not based upon the tetrahedral parent. And then you have structures which have 2 non-bonded pairs and 2 substrates, and give you an AX2E2. And again, the angles that are generated with the substrate are what defines the geometries. And this is called pyramidal. This is tetrahedral. And this one, as we just looked at a minute ago, should be easy enough, bent. So you're beginning to see the pattern that I'm trying to develop with you, and they're all evaluated the same way. So with this, I want to apply this to methane, and then ammonia and water, and show you that this one is based upon the AX4 parent. Now, you're not going to be told the systematic thing like this. You've got to figure it out on test day. But you can count on this to be no non-bonded pairs. This one has one, and this one has two non-bonded. The bonded pairs is 4, 3, and 2 as you go across. The non-bonded pairs is 0. You can figure the valence minus the 4 substrates over 2, and you'll get 0. But if you do the valence minus substrate over 2 for this structure, you'll find out it has one non-bonded pair. And over here, if you do the valence minus substrate over 2, just like I showed you, you'll have two non-bonded pairs. But when you add these together, they all add up to 4, which means all of them are based upon the AX4 parent. And you just have to allow one of the bars in the tetrahedron as a non-bonded pair, and then you have your hydrogen, 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 and your nitrogen in the middle. That's ammonia. It's a pyramidal geometry. Whereas water, you still have the tetrahedron, but you have two non-bonded pairs, hydrogen, hydrogen, and you have your oxygen in the middle. So this is an AX3E for this one. This is an AX2E2 bent. So water exists as a bent geometry, and you'll find out later when we get to states of matter, that's the key for understanding the polarity of water, and why water is a liquid is because it creates a dipole because of its geometry. And the geometry of ammonia is a pyramidal structure with available electrons up here, and they're very reactive. And hence the ammonia derivatives and stuff are very reactive because you have a negative charge that's open to everything. But when you get over here to methane, it's a regular structure with hydrogen, 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 carbon in the middle, and so it's a symmetrical all the way around. And this is reason methane doesn't form. The formula weight of methane, 12, 13, 14, 15, 16 atomic mass units, 16, 17, 18 atomic mass units. They're approximately the same between the two, but this one's a liquid at room temperature, and this is a gas. Why? Because of the geometry, and the attachments are distributed symmetrically in methane, but not in the water, and it generates the dipole, and dipoles attract positive negatives, and that's why water's a liquid in the room temperature state. You know, solid, liquid, and gas, but anyway, we'll get to that later. But you can tell a lot about the nature of the structure and molecule and chemistry and physics of it just from its geometry. Okay, we'll finish this, the VSEPR theory. I'm not going to start the valence bond theory until tomorrow morning. And let you digest this one. But I got two more examples. I got the AX. And we draw the little lazy triangle up and down, and then there's your 5 bond possibilities where we can put the electron pairs in that structure. Well, here we have bonded pairs. Well, of course, that's the attachments to the central element, like this. And then the non-bonded pairs, 0 will work out on this one, valence minus substrate over 2. Add those together, and you have a parent, which is a 5. Sum of those two, 5, and that gives you an AX5 parent. And geometry. So the parent and geometry are identical in this one, and it's the trigonal bipyramid. And so we would draw that in this configuration, and your substrates are all attached to bonds. And so you have 5 bonds to that central element. Now, there are only 2 per bond, 2 electrons per bond, but they're 5 bonded pairs. Now, when we go over to the SF4, we have obviously 4 bonded pairs, but when you do the valence minus substrate over 2, you find out there's a non-bonded pair there. And so adding those together gives us an AX5 parent, but it has a non-bonded pair, and so the geometry is based upon this AX4E. Okay? And the name of that, I'll show you, it comes out of the geometry. Again, we have to start by drawing the parent structure first and the possibilities of that. Now, we've got 1 non-bonded pair in this. Now listen, this is a rule that you got to remember. In the AX5 derivatives, if you wind up with electron pairs, they are placed in the plane of the triangle first, not above or below. That means that if I've got a non-bonded pair, I have to put it in here somewhere. And then I have attachment substrates in all the other positions, 1, 2, 3, 4. And if you look at this from the side, it looks like a seesaw with that non-bonded pair sitting up here, and that's exactly what it's called. A seesaw geometry, I'm sorry. It's called a seesaw geometry. You look on your handout, and you see that seesaw shows up at the AX4E right here in your handout. But that's how you get there with this, and looking at it from the side, here's your central element, and you get your attachments in those positions. But I like to draw it out like that to see it a little bit better. And so this is called a seesaw geometry, and it's a derivative. Again, the attachments define what the geometry is, not all the non-bonded pairs, but you've got to look at them to put them in there. This one has 3 bonded pairs and 2 non-bonded pairs. It's still an AX5 parent, but it's an AX3E2. And so when you start putting electrons into this, electron non-bonded pairs, they have to go into the plane, so you'll have 2 non-bonded pairs in the plane, and then you have your substrates here. And if you look at that, the structure of that is a T-shaped. So you can see how it goes in a T-shape right there. And that is an AX3E2. But after you draw it out, you get used to drawing these things out and look at how they are attached. And remember, they go in the plane first in this parent structure. You'll see the T, and remember that geometry. In the last one, we have 2 attachments, 3 non-bonded pairs. If you work it out, it'll show up 3 non-bonded pairs, which is an AX2E3 geometry, and this will be a linear, AX5 parent, sorry. 5 parents with an AX2E3 geometry, and this comes out linear. I forgot to write T-shaped. Linear in that, because when you draw your structure, like that, all of the positions in the plane are full. And you put the substrates above and below the plane of the triangle, and you can see clearly the linear geometry. And so that's how you break those down. The next one is the octahedron, which will be the AX6. So the issue in the non-bonded pairs with the octahedron is they will go above and below the plane first, in the above that lazy square I was telling you about, instead of in the plane first like an AX5. So you have to separate those and learn that fact. If you determine it's an AX5 parent with some non-bonded pairs, you have to put them in the plane. But when you see the next one, it's the non-bonded pairs will go in the above and below the plane of the triangle that we draw. So we have an AX6 parent with an octahedral geometry or structure for the parent, and that is drawn out with a lazy triangle as I showed you earlier. And then you have radials going out from the central element to the substrates. But remember, if you wind up with non-bonded pairs, you want to put the first ones above or below, and then if you have two non-bonded, it'll go above and below, and then you name the geometry, which we were about to do. Let me get my examples up here. SF6, what do I do with my list? I can find them. So we'll work with SF6. XEF4, and I'm going to throw in ICL for the polyion, which you'll look at. Okay, so bonded pairs, easy enough, right? 6, 5, 4, and 4. Okay? Non-bonded pairs, and you work out the valence minus substrate over 2. You'll find out this one has no 3 pairs. But the IF5 has 1, xenon tetrafluoride has 2, and ICL4 has 2 as a polyion. And so the parent is an AX6, and the geometry is also an AX6. And so hopefully by now you're seeing the pattern that I'm trying to teach you. And so that's an AX5E1, AX6 parent, sorry, an AX5E geometry. All of them are AX6 parents, as you add the two bonded pair, non-bonded pair, and so this is an AX4E2 and AX3E3. So from that, we need to draw out the geometries of each one based on what I've shown you. And so we would put the fluorides in all of the positions here, and it would be a regular tetrahedron as a geometry and parent. But when you get to the IF5, you still have to start with the parent and draw it first, and put your substrates in the, well, you put the non-bonded pair, say, I'll put it below just for argument, and then show you 1, 2, 3, 4, 5 substrates. And this is called a square pyramid, sorry. Next two will be square planar. And so you get to AX4E2 in the xenon tetrafluoride, and you draw the same figure, but both above and below the plane are saturated with non-bonded pairs, not saturated. And this is called a square planar. You can see on the handout. And the same way over here. Now, in this one, you would apply valence. I'll do that one out. Here's you have the chloride, 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 non-bonded pairs. But this is a polyion carrying a negative charge up here. So if I took the valence of this, it would be, well, actually I have 5 halogens. Okay, 75 is 35 plus 1, that's 36 on that structure, because I had to add 1 electron because of that negative sign. And then the substrates, you have 4 substrates, 4 to make 32. And then so 4 over 2, and so you have 2 free pairs, or non-bonded pairs. And so that's where that matches the AX4E2 type geometry. Don't have anything that goes any more complex than that. But if you have to go into it, there's a controversy in, well, if you put a non-bonded pair in there, where would you put it? In the next. If you put it right here, then you have a T-shaped. Or if you have 2 non-bonded pairs like that, you could either have bent or linear. So it gets kind of weird after that. So that's probably the most complex you'll see on the exam right there. The ICL4 negative or something like that. When we talk about complex molecules, we're talking about more than one center. In everything I've given you so far, it's just been a binary, say a center plus the attachments, the substrates. But here you have to isolate each center and look at the substrates, that what's attached to that each center. For example, if I took this, and I'm just making up a molecule here. Oh, multiple bonds. I forgot to. Let me pause. Multiple bonds in the VSEPR theory. I forgot that. Everything's been single bonds. Okay, here we go. And then we'll do the complex and finish. For the sake of defining geometry, at a given center, in other words, we're talking about the binaries, AX at the center A and with the attachments. For the sake for defining geometry at a given center, assume multiple bonds or single bonds. That's both double, instant, triple. And geometry is only single bond attachments. Okay, what that means is if I have acetylene, or if I have ethylene, you'll find out I could draw a Lewis structure that looks like this. The AVO Beck would give me that Lewis structure. Using the rule I just gave you, if you make this double bond into a single bond mentally. It's not really changing or doing anything. It's just a way to tell what's a center. This carbon is carbon number 1, and this carbon is carbon number 2. What you do is you define the geometry around carbon 1, and then go to 2, and then if there's more, 3, and on up, like that. So when you look at this, carbon 1 has 3 attachments. right there. And since it's an AX3 parent structure, as a matter of fact, carbon-2 does the same thing in that it has 3 attachments to carbon-2. Hydrogen, hydrogen, and then the group over here in that one. So that one is also an AX3 parent. So the geometry about the carbon-1 is trigonal planar. And trigonal planar around carbon-2. So when you draw this out, you can do it this way if you wanted to. And show the height. Actually it rotates, but you can see the trigonal planar geometry between the 2 carbons as I'm drawing right here. And then simply put in your double bond between the 2 center carbons. If it's a triple bond like in the settling, this would be trigonal planar about the carbons here and here, as I've just shown you. Now, what if we went to settling? It's C2H2, and if you went through the AVO back, it'll give you a structure, H, triple bonds in between the carbons, and I think I did this example yesterday. Okay, now in here you also assume that your triple bond is a single bond, and this is carbon-1, carbon-2. And you look at the attachments that surround carbon-1 here and here. Whereas carbon-2 is 1 and then 2, like that. But so that gives you an AX2 around each one of the carbons, and those are linear geometries. So it's 180 degrees in this structure. Around, you have to take one carbon at a time, or one element at a time, and look at how the geometry evolves from that. Okay, with that, now I can do complex molecules and show you how those are untangled in the VSEPR theory. Okay, so I'm going to make up a molecule, like I said a minute ago, but here is the idea. So we run out the AVO Beck, or somebody gives you the structure in the Lewis form. And you draw this out. There's your nasty molecule that who knows what it is. So in the evaluation of this, you go left to right or right to left or whatever, but you have a line of symmetry going through the molecule with substrates attached around the structure. So this is carbon 1, then 2, 3, element 4, 5, 6, 7, 8. So how does the geometry vary as you go left to right on this molecule? and I'll try to draw it to the best of my ability. So starting with the carbon 1, we see what? 1, 2, 3, and everything back here to the right is an attachment to that carbon 1. So if we took carbon 1, we find that it is an AX4 parent right here, based upon this grouping right here. Now if we go over to number 2, we see it has a double bond in it. Now what does that say? You make it a single bond just for geometry. So there's 1, 2, 3 bonds with 3 attachments. So you take this portion as an attachment, the hydrogen, and this methyl group is called over here on the left, and so that's an AX3 parent right there. Move over here, and that's also an AX3. If you can see that 1, 2, 3 attachments. So you continue to move down the list. Now here is 3 bonds with a non-bonded pair. That's 4 electron pairs. So around the nitrogen, we have an AX4 parent. So you have to draw it out in a tetrahedral configuration if you get to the nitrogen because of the nature of that system. Here is an AX4. 1, 2, 3, 4. Now, what would the geometry about oxygen be? You have 4 pairs of electrons. Again, you'd have to draw out a tetrahedral configuration. That's an AX4 configuration around oxygen. But here, when you get to this is called a carbonyl. When you see a carbon double bonded to an oxygen, very prominent structure in organic chemistry and organic acids. It has just 3 bonds to it, so you'd have to draw a trigonal planar AX3 around that one. And of course, chloride's by itself out there, and so it's just an attachment to the carbonyl structure. So as you try to draw, you want to draw this kind of configuration, starting with the tetrahedron on this end, and you'll have your hydrogens, hydrogen, hydrogen, and then you go over to this carbon, but it's a double bond, but it's a trigonal planar like that, and then it'll come off to the nitrogen like that, which is a tetrahedron, a pyramidal with the, but you still take into account the tetrahedral geometry. That's your AX3 in here, and then that would go off to a carbon tetrahedron here, and you got a couple of hydrogens, put them right there, and then you come off to the oxygen, but it has to be lined up as a tetrahedron. Let me see if I can get you a tetrahedron out of this. There we go. And you got double bond, and then this one in the back goes off to that carbon back here in the carbonyl. I'm going to put that carbonyl down here so you can see it. I'll put the other pair right there. But it'll come down here, and then you'll have a trigonal planar going back up to the chloride. And down here, to the best of my ability, there's your trigonal planar, and so your molecules all laid out like that. And this is planar, and this is an open to a tetrahedral geometry, if you can see that. And so that's what I'm talking about. In complex molecules, you have to kind of go one step at a time through each element that constitutes the central element of the, at that point.